received a number of questions. What does TSP mean? You will learn that throughout the talk. It has some meanings, and the real one will be revealed in the end. This talk will be very different from the previous ones. We'll have no quasi-convexity or partial differential equations, very simple stuff, but maybe sometimes useful. And okay, so it could have been state of the art, but state and art was, of course, something I thought about. So there will be an introduction, and there will be some history of TSP and some variants, some applications. Whether or not I will do modeling, I don't know yet. Heuristics, how combinatorial optimizers do it. And then there will be something on art, astronomy, and astrology. Okay, so the introduction begins with optimization, and what I will be doing is giving you kind of a survey of some type of optimization problems. There's this pointer. Oh, yeah, there's a pointer. A number of people here are concerned with this kind of problems, where you want to maximize or minimize some function f, subject to some equations and some inequalities. Usually you're in the reals or some plus some set, and that is what we call a general nonlinear program. And this is very difficult, and you are assuming here something about this function. In theory, you usually assume that these functions are, say, twice differentiable, and the best relaxation you can sometimes handle is piecewise linear, piecewise convex, piecewise something, piecewise differentiable. It's very difficult and not so easy to handle for a large scale. That is nonlinear programming. And then you do this, you make it problem easy by requiring that these functions g, h, and f are linear. So it's just a vector multiplied with a vector of variables, a linear equation system, and inequality systems. You're usually working in the reals, sometimes in other spaces, typically the rational, but that will not be concern us here. That's a linear program, and linear programs are very important for from various points of view. And what I will be interested if you add in addition this constraint, namely that your variable should be integer or 0, 1. I mean, a special case of integrality, of course. And these are linear integer programs, IPs. And sometimes you require that some of the variables are integers, some may be continuous, and then you have a mixed integer program. So this is the type of problem I am concerned with most of the time. And although I will give you now, I will talk about a very special integer program, I will basically give you also a survey how you solve these types of linear integer programs or mixed integer programs in general. So what is now combinatorial optimization? Combinatorial optimization, I've just formulated in words. You have a finite set E, and you have a subset I of the power set of this finite ground set. And I is the set of feasible solutions. In addition, you have some value, cost, a length, or whatever. For each element E, you have this value C of E. And you would like to find among all feasible sets a particular set I that has a total value as small or as large as possible. And the total value is nothing but the sum of the values of all elements in the set. Now you can write this now in formulas, and then you have more mathematical flavor. But this can be told to everybody that has no idea what mathematics is about. And a particular issue is, this is a subset of the power set. So this set is usually very large. And the question is, how is I given? If I is given explicitly, the problem is easy. You just scan through all the elements, and you choose the best one, and you're done. But this is not the case. These sets are usually given implicitly, and that's what I will talk about now. Namely, here are special problems that you may have heard of. Namely, you want to find a spanning tree in a graph with minimum length. You want to find the shortest path in a directed graph. You want to find a maximum matching in some graph. You would like to find a cut separating two given nodes in a graph or digraph that has minimum capacity, or you look for a cost minimal flow through a network with capacities and costs on the edges. These are typical combinatorial optimization problems. And they are simple in the sense they are polynomial time algorithms. And they're not only polynomial time algorithms, you can really solve them efficiently. So the most difficult among these is this one here, cost minimal flow through a network. And for instance, you can go to the website of my institution, the Konrad-Zuse-Zentrum, and you will find there a program, MCF, Min Cost Flow, that solves in a few minutes, say, 100 million variable problem on a laptop. So these are really fast algorithms exist that you can use in practice. And then there are some others that look the same. And here comes the first interpretation of traveling sales. TSP is the traveling salesman problem. And that's a prototype problem I will focus on. And there are others, like location and routing, set packing, partitioning, covering, max cut, linear ordering, scheduling, node and edge coloring. These problems, I don't introduce them in detail, are hard in a very precise sense, namely using complexity theory from computer science. You can prove that if any of them can be solved in polynomial time, all the others can be solved in polynomial time. So they are particularly hard problems, and they also appear hard in practice, but nevertheless they appear in practice. And you cannot just say, well, it's hard, I don't want to solve it. People want to solve them. And so the whole theory that I will outline later on is concerned with solving these problems in real practical cases. So what can we do nowadays? So here comes the traveling salesman problem, the TSP. You're given n cities, again in words and distances between the cities. You want to find a round trip through all the cities, visiting every city exactly once, so that the sum of all distances traveled is as small as possible. Everybody can understand that. And in fact, this is the best known optimization problem, I believe, by people who do not know anything about mathematics. So I'm doing a lot of practical work, and I'm having contact with many companies. And what very often happens is somebody phones me up and says, I have another traveling salesman problem for you. But it has nothing to do with traveling salesman, it's just combinatorial optimization, but they think this is traveling salesman. Okay? Now there are several versions of it. The symmetric TSP, the STSP, is the problem when you have symmetry in the distances. From I to j is the same distance as from j to I, and asymmetric if this is not the case, and both problems exist and are serious practical problems. Now, you can turn this into mathematical formulas or mathematical notation. So one version is you're now looking at a complete graph on n nodes. This is V, the node set, and E is the set of all possible edges between every pair of nodes. That's a complete graph. You have this value CE on every edge. And then you define what a Hamiltonian cycle or a tour is, that this is a cycle that covers every node. And then you would like to find a tour or a Hamilton cycle of minimum length in the set of all Hamiltonian cycles. So that would be a graph theoretical notation. You can also talk about permutations, namely if you have you find a cyclic permutation of the numbers 1 to n, so that the sum of these values is as small as possible. And you can keep on going. I mean, I can give you 10 more definitions of this type, but the question is, does it help at all to solve traveling salesman problems? That's the important part. And this is what I would call the modeling issue in optimization, namely, what is the right formulation for an obvious, simple problem so that you can get a computational handle on it? And all this is completely useless from a practical point of view. You would like to have some machinery, and this machinery I will outline that is based on using the integer programming technology. Here is a homepage that I give you, tsp.gatech.edu, where they just tell you more about the TSP. Here, for instance, is a traveling salesman tour. And this, in fact, these circles here and modes provide a proof that this is optimal. I will not explain to you this in detail. The reason for that is that for this particular TSP, you can find a dual problem, and you can actually describe these dual problems by means of modes and circles around nodes. And those who know about the details of the duality can tell you that is the optimum solution of this tour. The unfortunate thing is that this does not always exist. So you don't have an easy proof of optimality, and that makes the problem hard. And just to remind you of that, here is the Clay price is $1 million. So if you can solve TSPs in polynomial time, you will get $1 million from the Clay Foundation. So now there's always interest, at least I am very interested in history. I like to study this, and so I've looked into the history of the TSP. And the typical, what you find typically in the books is that Sir William Hamilton is one of the founding fathers of TSP theory. Namely, he introduced what we call Hamiltonian cycles today. And this is a picture taken at the library of Trinity College in Dublin, where there is a box with a game that Hamilton invented and tried to market about 100 and some years ago. He was not very successful. That was about finding Hamilton circles under special conditions, but there was no distances involved, and this is Hamilton. But then typically the traveling salesman itself is mentioned, the inventor is Karl Menger, who talked about this in Vienna and later in Harvard, and he got people interested in it, and then in Princeton there were more talk about Merrill Flood and Hassler Whitney, so this became a problem to talk about. But, as usual, things are different in the real history. So here is a book, The Traveling Salesman, How He Should Be and What He Has to Do in Order to Get Jobs and Have Success in His Business. So that's a book from 1832 in German, about 100 years earlier than all these other people I mentioned. And I took a page, some 320 or so, and that's an English translation. By proper choice and scheduling of the tour, one can gain so much time that we have to make some suggestions. And this guy explains what to do. The most important aspect is to cover as many locations as possible without visiting a location twice. And actually, the whole book, or end of the book, is about, he gives example tours, how to travel if you start in Germany, in Frankfurt, and go around, what is the best tour. This is very interesting to see shortest tours in Germany. So, I mean, 100 years before anybody had ever talked about the traveling salesman problem in a book for traveling salesmen. So, but we go back. This is Ulysses, and this is the Greeks. And if you actually read Ulysses, Homer, actually, I think Homer wrote a travel guide through the Mediterranean, if you look at that, and he coached it into a criminal story. And he very precisely described all these places, but he would probably have in mind that you'd ship you around the Mediterranean, make it a little complicated, and tell you exactly what's going on in Java, Gibraltar, Ithaca, Troya, and the like. And of course, if you want to follow Homer's tour nowadays, what would you do? Well, you rent a helicopter and do the shortest round trip to see all these places. And here's the distance map of of Ulysses' trip. And that would be the round trip we would do today. So the traveling salesman would be Ulysses, and that would be his Ulysses tour if you want to do the shortest round trip. But actually, I think it's even older than that. And if you think about your childhood, you remember these things, drawing by numbers. You get these dots and numbers, and then you have to connect these numbers, and something suddenly comes out. I've drawn some of these. Now you keep on 1, 2, 3, 4, 5, 6, and you keep on going like that. And you can finish off. And if I have actually inputted some of these figures, and it turns out in most cases these were traveling salesman tours of the picture to be drawn. I found that very interesting, and that was one from one of the books I found at home. But here are more. There are English ones you can find in the literature, and the name is used as drawing by numbers. And I believe that was invented, I mean, by the Neanderthals. And so traveling salesman is a really old concept. Okay. And there is TSPs actually in the sky. And I will come back to that later, because I think that's a very interesting story to find the graphs and TSPs in the sky. So astronomy, astrology, and art have something to do with that. If you want to know more about it, here are two survey books. That one is from '85. That's still pretty good book. And here's one from 2002 that have articles on all kinds of aspects. And if you I just went into Zentralblatt Math, and I found 880 entries just having traveling salesman in the title. And now you have it in 2 L's and 1 L, and you get even more. I mean, traveling is not so clear how to write it. So, what is TSP? There is not only one. We have already mentioned symmetric. That means if you go from A to B, it's the same distance as going from B to A. Asymmetric if this is not the case. And now you have something like precedences or time windows. That is quite important in practice. Precedences means you have to go to one place before another. And you get basically a directed graph in addition to your tours, where it tells you have to go see this one before that one, and so on. It gives you additional constraints. And time windows, you can imagine you want to deliver something in a city, and you can only go to the central square between 8 and 10 in the morning or something like that. There are time windows like that come in. And the question, and this adds additional constraints, and sometimes additional constraints makes problems easier or harder. You never know what happens. In this case, it makes them infinitely harder. And that's a strange thing. Then there is the online TSP. I will explain that soon. Then there is the MTSP. M often comes in when you have, say, trucks that have to go around, and trucks have capacity, and you cannot pick up everybody. So you have to send out M trucks, and jointly you would like to cover all of them, and that would be the M multiple traveling salesman problem. But you maybe leave open whether you have M or less than or even to M, something like that. Price collecting TSP is another nice variant with some applications, namely, when you show up at a certain place, you may get some money, but the money may depend on the time you arrive there. So the order is also important. It's not the shortest round trip. You also would like to collect money, and you would like to maximize this, collecting that money. And here is another interesting variant that looks similar, but is very different, the Chinese postman problem. The Chinese postman problem comes from the Eulerian Königsberg problem, going over the Königsberg bridges. And Chinese mathematicians in the 60s, Mei Guan, made an optimization version of that. And since people thought this is the only Chinese mathematician, they called them Chinese postman problem, which of course is a ridiculous idea, but this is how it entered the world. Namely, you would like to make a round trip, not covering every node, but covering every edge, at most one. And that's a typical example, is garbage collection. What is happening? It's about garbage collection. Namely, when you collect garbage, you don't have to meet nodes, you have to go along all streets, or a postman has to go along all streets and pick up all the posts or deliver all the posts. And this has an interesting story, namely, if the city is undirected, there are no one-way streets, or if the city is directed, then it's easy. But as soon as it's mixed, there are some one-way streets and some non-one-way streets, the problem becomes hard. So this is not intuitively clear, but you can prove it. So, and then you have generalizations, bus, truck, vehicle routing, routing with capacities and combinations of all that. That comes up all the time everywhere. So if those who are interested here in Campinas is Pablo Moscato, who keeps the TSP bib homepage. And if he has everything you ever wanted to know about the TSP or don't want to know about the TSP, tons of information you can look up. So go to TSP bib on Google and you find all the information you want to see. Now, I would like to give you some applications so that this is the real world. My favorite application and coming up frequently is in the design of integrated circuits or printed circuit boards. Namely, you see here, there are these little dots, and in these dots you have to drill holes. And the holes either have to be drilled mechanically or using a laser beam. And see, one machine that may drill 7 plates in parallel, and there may be a stack of 20 of those, and such a machine costs $1 million or so. And that is in the processing plant of many of the electronic companies. And what they would like to do, the drilling as fast as possible in order to process more material. So here is such a printed circuit board. And I like this example in particular for the beginning students, as some typo, but forget about it. Namely, what is the length of a move from this point to that point? Well, the typical mathematician would say, well, that's the Euclidean distance, but that's not how machines move. Machines have 2 motors. One moves in that direction and one in that direction. So what you do is you move a motor from here to there until you hit it, the coordinate, until here, until you hit this coordinate, and then you are arriving at this point, and that's the maximum distance of the 2 moves. And the moves are, of course, not linear. It accelerates, goes at high speed, and brakes. And so there are complicated norms in practice showing up that you have to take into account, which are not Euclidean. You can show that these norms come up in the real world. And here is this problem. That was the industry solution, and that was solved. That was a world record we will later see by Padberg and Rinaldi. It was 50% better than the manual solution. And so that gives some improvement in practice, of course. I'll give you, so I have worked with my students, Jünger and Reinhold, on that a while ago. And here I've just copied out of a report for Siemens. And at some Siemens plants, our software is still running. So here's like a board, and that's what the solution was before, and that is the solution after. Why are they going several times? That means they have 7 different drills. So the drill, they go here, pick up a drill the holes of certain size, and come back, pick up the new drill, and keep on drilling. So these are maybe 4 or 6 or 7 traveling salesman problems for different types. Here's another solution of that type. And here's an example for a laser drill so where you have a mask and you have something down here that moves around. To give you examples, here are examples from practice, 2,500 nodes that you want to drill. And you typically have limited running times in practice because you do this online. They bring in a new printed circuit board and drill it. And here are the improvements we obtained in practice. So that's sometimes it's small, 50%, but sometimes it's between 50 and 60% compared to the practical problems in practice that they've used before. Here I have a film, maybe I'll run it quickly. That is a, why doesn't it run? Okay, I could even switch. Oh, you don't hear that anyway. So this is about stacker cranes in a factory, and we'll see that soon. That have unloaded moves, pick up something, move it in here, and come, then go unloaded, pick up something else, and go around. So that is in a typical warehouse. You have problems of that type coming up all the time. And this is an online problem because you do not know in the morning what are the jobs coming out through the day. And the issue is, how do you run your factory, how do you run your machines so that you are fast, but the boxes are not staying somewhere and never be picked up. So you have certain time windows and so on in that business. And this is a practical problem we solved also in a Siemens plant. And here's a big factory of Herlitz at Falkensee in the suburb of Berlin. And you can see some real stacker cranes here that move boxes around. And so they have the software that we developed running there to optimize their production. Here's another example, namely in Europe we have now the rule that electronics garbage has to be collected, so it has to be recycled. So the companies that are selling electronic equipment have to pick it up and recycle it somewhere. So they have to introduce now a network of recycling factories and collecting mechanisms and so on. And at the logistics chair in Berlin, they have made a study of the logistics of collecting this electronics garbage. And here is, for instance, now a location analysis of making 1, 2, 3, 4 distribution centers or collection centers with local tours. This is salesman problem, collecting this garbage. This was done by my daughter in her master's thesis, and she actually used the software that we developed, and she just picked it up and did the stuff. So I found that very interesting. She did not study mathematics. She is an engineer, and used the machinery in order to compute good solutions for garbage collection. Here is her mathematical formulas, and we'll come back to that later on. So that's the mathematics behind it. Here is another interesting problem, but I would like to tell you, it's the online traveling salesman problem, or traveling salesman. In Germany, you're on the highway, you get stuck, you have a problem, you call the German Automobile Organization, there's a dispatching center. They get your data, transmit the data to somebody here. The dispatcher figures out which car goes, it's a yellow angel, and tells the guy, in 35 minutes, we'll come and pick you up and help you. We have 5 dispatching centers in Germany. We have 1,700 cars running around on German highways. and you have to dispatch them all the time. And they were not doing a good job, and the ADAC was losing money, and now we have set up a software system that does that automatically. So when you break down on the German highway, you call them up, we compute which car will go and pick you up. Okay? This is online, because you see what the difference now is. You call the guy, and the guy has to tell which car should go. He cannot wait until the evening to figure out which is the best route. So among the possible decisions, he has to think about the future without knowing the future and come up with a solution that at the end of the day brings up a good cost. And that's a very difficult issue that mathematically is not well analyzed. This is a problem for online TSP. You start at 0, go to do some job, you get another job, and you would like to find a fastest tour, serving all requests, and you would like to be not too far away from the optimum. Well, the optimum will always compute in the end of the day, but so what you could do is you let the day go, and in the evening you compute the best tour, and then you just let the cars go and do the optimal routing, but this is not very helpful in practice. So you would like to have some C-competitive algorithms. So the algorithm solution is only 40 times worse the optimum in total. So that's a big research area right now, and we've done some contribution to that, but I will not go into the details of this. So let's show you some of the applications, and there are always implementation challenges where you can, when people compare algorithms and the like. Modeling issues. This is something, I will not go too much into the detail, and this is about this precedence-constrained asymmetric traveling salesman with time windows. This is exactly the problem that comes up at stacker crane optimization. And what I would like to tell you is a little bit that we sometimes do not know what is the right linear programming relaxation. Here's a paper we wrote about it. And what we did is, well, I will not explain this. We wrote down 3 models, 1, 2, 3, and here are them combined. Okay? So the only thing they have in common is the set of solutions is the same. So whenever you have an integral solution of this problem, you can derive an optimal solution of the asymmetric traveling salesman problem with time windows. Here also, here also. But there are different variables involved, different inequalities. It's a completely different approach in writing down the inequalities. And this contributes to what I said in the beginning. What is a good mathematical model? A graph theoretical model, an algebraic model, and these are all 3 integer programming problems. They are all the same, I mean the same solutions, but what will it help solving them? And so what we tried to do, what we did is, we made a thorough investigation of the suitability of these models for practical problem solving. Of course, theoretically, they're all the same. The problem is NP hard, so from the asymptotic analysis, they are all difficult. And we did all the machinery that we know and threw that all in what we could do. And the result is extremely uneven performance. The first model, without telling the detail, was really bad. It was hopeless to use this. The model 2 was the best on the average in 1 in 16 of 22 test cases. The third model was the best in very particular situation when there are only few active windows. And the issue is, how do you know that in advance? So this is one of the problems we have in practice. I told you, people come to us and say, we need to solve something. Right now, Volkswagen just called me recently. We do laser welding on the Golf, and we have a problem with our laser welding robots, and we need to do different sequencing. Well, can you solve it? Well, we could solve it within 3 months or so. We could come up with something, but we had 4 or 5 different models. Which one is the right one to attack? And it does not mean that all this comes automatic. You really have to look into it, do some research, and think about it. And this is something that is very open in the optimization approach. What is a good model to solve a problem in practice? So here is a few examples. You'll learn what that is. And if you go for this 41 city problem, and here's a 67 city problem, here I needed 1 million more than 1 million cutting planes, ran over 4 hours and have not solved it to optimality, namely 10% of optimality. A 67 city problem was solved to optimality in 6 seconds, and I have no idea why that is so. And there's a big problem we could solve with 127 nodes, and one with 43 we could not solve. I just don't know why it is so. It's difficult. And I mean, from a theory point of view, of course, it is clear that will happen. But in practice, this is something that is unknown, and we are still trying to understand what's going on there. So what I would like to talk to you a little bit about is heuristic approaches. That's something we haven't done so far here. Namely, you have a problem, it's very big, and you would like to solve it quickly. And the exact algorithms will be unable to solve it, so you come up with heuristic ideas. And in general, for real-world hard combinatorial optimization, they are often too large for exact algorithms. And then the customer may have strict time limits. So what often happens is somebody sits in front of the screen and wants to solve a hard problem. He's not willing to wait for more than 5 minutes. And you have to solve something in 5 minutes, period. So you come up with your best idea and do this. You can tell him, but I can do more in 1 day. He said, in 1 day, it's too long. I cannot do it. He wants to see something quickly. So we need heuristics. But of course, within heuristics, you run exact algorithms. And again, something that is very unclear right now is a good decision guide. Which heuristic will most likely work well on what problem? This is also very open and much discussed in the literature. Usually people claim things that they cannot really give proof of. Why is, and what we do in practice is we find primal and dual heuristics. So the primal heuristics find a good solution. So like in the traveling salesman problem, we manipulate the problem and find a tour. And of course, this is an upper bound for the minimum. You just can't compute the value. And you would like to try and find a good one. But the dual heuristic is just the other way around. Namely, if you minimize, you want to find a lower bound for the solution. And now you have a lower bound and an upper bound, and the optimum value is in between, and you compute the difference or the relative difference, and you can provide a quality guarantee. So quality guarantees is the subject of a lot of research in theory, but in practice, you would like to have clear numbers. My solution is only 5% away from the optimum. What that means is you have a lower bound and you have an upper bound, and then the relative difference is 5%. Optimum is in between. Say that's fine, depending on my data. But if it's 5% is $10 million, then you would like to keep on working, okay? But if it's only peanuts, you just finish and say it's over. And the problems are of different type. And here is just a list of, say, names of heuristic approaches that have been used in practice. Greedy algorithm, that's a simple one in the traveling salesman. It's called also nearest neighbor. You start at a node and look for the nearest neighbor, go to that. Look for the nearest neighbor not covered, go to that. Keep on going and finish, okay? What can you say about this? The insertion exchange algorithm is something easy. You have a tour and then you make a swap. And you may be shorter and you have made a swap and you do that. Good algorithm. Neighborhood search, variable neighborhood search, simulated annealing, taboo search, simulated tunneling, neural networks, and so on. You can fill, the literature is full of that, particularly now in the engineering literature and in the computer science literature. Here's more about it. Genetic, evolutionary algorithms, swarm, ant, multi-agent population, memetic, fuzzy, and so on. But these people make claims you just can't believe. And I would like to give you one claim that comes from a very respected journal, Science. Yeah, I mean, if you are a biologist and can publish in Science, this is the best possible you can do. It's like Invenciones. We have Michel here. And I just click on this. And Invenciones, here it's from, says, DNA computer helps traveling salesman. Okay. You think that something has to do with traveling salesman. And the whole article doesn't say a word about traveling salesman. It just says here, the group worked on a relatively small-scale satisfiability problem with 16 possible solutions, all of which they encoded as a strand of DNA. That was it. It has nothing to do with traveling sales. They just used to advertise it, and then they used DNA to compute the best among 16 solutions. Okay, and that was DNA helps traveling salesman. And you just can't believe things like that. And that goes on. I mean, you don't know these people, and I don't know these, so I can hit them here. And it's just amazing what you sometimes read about this. So the same happens with multi-agents and population heuristics. They all claim they can solve everything, and then since I am the editor of certain journals, I tell them, here is a database, tsp.lib. There's a library with a couple of hundred problems. Solve them, and then you can compare with what has been done by others, and then these usually give up and publish it in engineering or somewhere else. Or even a psychologist comes up. He has the method of divine intuition. That's wonderful. But you have to have this trouble with these people all the time because they claim they can do everything better. And so you have, well, it makes it difficult, but it's okay, you can solve it. Now, I would like to give you an analysis of one heuristic. So that is, for the time being, and now for 30 years, the best heuristic with respect to worst case behavior. Now, worst case behavior is the following. Here's the optimum, and you would like to prove that all solutions are within a certain % of the optimum, okay? When you run the heuristic, it's only, say, 100% away from the optimum. Number one is, you cannot guarantee that. You have to make an additional assumption, which I forgot here, namely the objective function has to satisfy the triangle inequality. Going from A to B, B to C is not shorter than going from A to C. That is a requirement I forgot to put. And the Christophidis heuristic does the first thing. He computes the shortest spanning tree. So here's an example of nodes down there. That's the shortest spanning tree. Number one. You observe that the shortest spanning tree, the length of that is a lower bound for the traveling salesman tour because among the possible spanning trees are all Hamiltonian paths. And then you add one edge, you have a Hamiltonian cycle. So a Hamiltonian cycle is never shorter than a Hamiltonian path. The shortest Hamiltonian path is never shorter than the shortest spanning tree. So that's a lower bound for the length of the traveling salesman tour. Then you look at this thing. The red nodes are so-called odd nodes. They have an odd number of edges going in. Here it's 1, 1. This is black. It's 4, 1, 2. 3 is odd, 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 and even. So these are odd nodes. Then you compute the shortest perfect one matching. That is this, that matches, so that connects two red nodes. Now there is a theorem in graph theory made by Euler already that says the number of odd nodes is even. So you can always find a perfect matching, and you can prove that the shortest perfect matching is no longer than half of the shortest tour of a traveling salesman. So this is shorter than the traveling salesman. This is shorter than half of the shortest tour of the traveling salesman. So the sum of these two is no longer than 150% of the traveling salesman tour. So you add these two up. So now is a collection of edges whose length is not longer than 50% more than the shortest tour. And that's an Eulerian graph, a connected Eulerian graph. And now you make a shortcut. Then you start, say, with this node, and you follow somehow this thing. Go along, and go here. And then you come to a node that you have already seen. You drop the node, go to the next. You take this shortcut. Then you go to this one. You have seen that. Go to the next, come here, and that is the tour is completed. So you make shortcuts, and that is the solution. That is the traveling salesman tour that comes out of this algorithm. And you can prove this is no more than 50% away from optimal. So just that is an easy analysis of these cases. And it's the world record for 30 years. Nobody can do better. But there has been a lot of research. So there is no polynomial time approximation algorithm for a traveling salesman, directed or undirected. Christophidis is a winner. You can look at average case analysis. There's something interesting. You can do probabilistic analysis. That's something really exciting, but not for practical purposes, for mathematical purposes. You take a square, throw in endpoints. What is the most likely length of the traveling salesman tour? You can compute it. It's 1.714 times square root of n with high probability. That's interesting. You can look at polynomial time approximation schemes, and there was a recent big breakthrough by Aurora for the case of the Euclidean distance traveling salesman. There's no polynomial time approximation scheme. But you look at all this with hundreds of papers, it doesn't help you solve traveling salesman problems. The best one is the Lin-Kernighan heuristic that in all challenges has turned out to be the winner in all experiments. And that's a heuristic you simply cannot analyze. Nobody knows what is the performance guarantee, but in practice, it always wins. That's how life is. Okay, now we come to the combinatorial optimizers. How do they do it? They look at now they go to geometry, namely we take the convex hull of all incidence vectors of feasible tours, and we investigate dimension, equation system, facets, and separation algorithms. So that is a research program. And when you are successful, you can try to transform this into codes and make linear programming approaches, which I'll explain to you. So here is the formal way. You take a vector chi, that's the incidence vector of a tour, and this vector has components ij. For each edge, it has a component ij, and the component is 1 if the edge is in the tour, and it's 0 else. Okay, so you have a 0, 1 vector for each tour. You take the convex hull, that's a polytope in Rn squared, basically, a number of edges. And then you can write down equations, namely in each node, one edge goes in, one edge goes out, so the sum of the edges going in and out is 2. And then you have so-called subtour elimination constraints, and that is the so-called linear programming relaxation. And when you look at this linear program and add integrality, then all solutions of that linear program are exactly the tours of the traveling salesman. And if you forget this 0, 1 condition and replace it by that, you can solve this linear program in polynomial time, despite the fact that you have here about 2 to the n minus 1 inequalities. So that's a big number of inequalities, but you can solve it in polynomial time. And here's an open, interesting problem, namely, what can be proved is that this linear program and the difference to the optimum is 3/2, but the conjecture is only 4/3 away. So there's a gap of 4/3 between these linear and this integer program. That's unsolved right now. There is a general theory how to derive now more cutting planes. So what you would like now to do is to describe the polytope given as the convex hull of some points by linear inequalities. And here is a general machinery, the Gomery cuts, but that simply doesn't work in practice. So you come up with some new ideas. I will not explain that to you. You look at these figures. There's a red ellipse and some yellow, a red and some yellow edges. And let's call a red one a handle and the blue one a tooth. And here is something more complicated. It's a clique tree, and it has some property. Namely, if a red one and another red one never intersect, a yellow and a yellow never intersect. If you have a red one, it meets an odd number of yellow ones, but always more than 3. And so on. There's some more connections, and the story is every configuration of that type with its extra requirements gives an inequality that defines a facet of the traveling salesman polytope, and that is such an inequality. But it shows that all traveling salesman problems need these inequalities. And there's an infinite number, and this is not all. Here's a list of inequalities that have been found in this research program, and this is incredibly many. But we are using this in the practical approach. And here I'll show you something weird. I mean, there are also some weird stuff. Look at this graph. That is the Peterson graph. Everybody in graph theory knows that. This is a so-called hypo-Hamiltonian graph. It has the following very strange property. It has no Hamiltonian cycle. But if you drop any node like this, then the rest has a Hamiltonian cycle. And that is not only for this one, it's true for all. And the question whether these graphs exist was non-trivial to prove. And that's the smallest that exists. And Yoshiko Wakabayashi from Sao Paulo and I proved that these set of edges with the right-hand side of 9 defines a facet of the 10-city traveling salesman problem, but not a facet for any bigger. So that means, and this is a general theorem that shows that if you find a hypo-Hamiltonian graph of 1,223 nodes, that is a particular unique property of this particular TSP and nothing else. So in order to describe the traveling salesman polytope completely, you need to know all hypo-Hamiltonian graphs, and it's completely hopeless. Okay? Nevertheless, there are wonderful surveys about the progress every 10 years or so. There's a huge body of literature coming up on this that you can look up. Just give you some numbers. If you look at the number of tours for 3, 4, 5, and 10 has 181,000, and we already know 50 2 billion facets of this polytope. But it's not clear whether this is the exact number. That's the number. So the growth of the facets is much stronger than the growth of the number of tours. But nevertheless, you approach the traveling salesman problem not via tours, but via facets. And that's the big winner, and this is a miracle. So what you do is, you're given a system of valid inequalities of exponential size. You would like to find separation algorithm that, given a point, checks whether the point satisfies all inequalities of a system, and if not, finds the violated inequalities, adds it to the system, and keeps on going. That is a separation and cutting plane algorithm. Here's an example. You have a convex set, you have a point, it's inside, fine. Now you have another point that's outside, and here you can find a cutting plane or separating hyperplane. There's another one. And here is the objective function, and Schreiber, Lovász, and I proved that if you can separate in polynomial time, you can optimize in polynomial time. And so separation and optimization are inherently connected via polynomial time algorithms. And that is the secret behind this approach, which I will not give you in detail. And there has been great success in finding polynomial time algorithms for various classes of facets of the traveling salesman polytope, and very good heuristics. And they're all practically efficient, and that's why they are used in practice. And there's powerful algorithms that now solve these kinds of problems, and I will show you now. Here is Germany. 1,500 towns we have, 15,000 towns. And if you look at this as a traveling salesman problem, you have 115 million variables, integer program. How to solve a problem like that? So that's the issue. And you do an upper bound, you run a Lin-Kernighan heuristic, you do a lower bound with the machinery that I just explained to you just roughly. And the hard part is the lower bound. And now the hard part exactly works like this. You do the equations, the inequalities, throw out the integrality, do the linear, replace this by upper and lower bounds, and keep on adding cutting planes. And the cutting planes are done like this. Now here you have, say, I cannot produce a picture of the TSP polytope. Here are the feasible solutions. These are the integer points, the yellow guys here. Here's the objective function. That's your optimal solution. You don't know how to find it. So what you want to do, you take the convex hull of the yellow points. You don't know how to find it. So you take a bigger set, a polyhedron that is bigger. You optimize over the polyhedron, find that optimum. You let a separation algorithm come. That finds a cutting plane, add the cutting plane, find a new optimum. You find a new cutting plane, find a new optimum, and you keep on going, and you hope you sometimes end. And this sometimes ends. And here is an example of a cutting plane for the traveling salesman problem, which is very complicated. And what you have to add in addition is branch and bound. Namely, you cannot finish out with this. You finish up with an LP solution that has a fractional value. You add, say, value 0 or value 1, and you branch and cut it into 2 pieces, and you keep on doing like this. And then sometimes you find an integer solution. The integer solution gives you an upper bound. An LP solution gives you a lower bound, and if the gap is 0, you are done. So that is the crucial aspect. And here is a real branch and bound tree for the largest problem solved to optimality, Sweden, 25,000 cities. That is a real picture computed by Applegate, Bixby, Quartal, and Cook. And that is the secret of solving these types of problems in practice. We are talking about a linear program with 150 million columns and 2 to the 100,000 constraints. And you only run a core LP of, say, 50,000 columns and 30,000 linear rows. And you must have algorithms that check that the optimum solution of this linear program is optimal for all the columns, and it satisfies all the rows. And you need particular algorithms to do that. And the secret is to find fast algorithms to run it and do this stable and come up with something. So here I show you this approach. This is exactly the approach that has led to the success. And here is the collection of world records. 1954, it was a 49-city problem. This is my PhD thesis, 120 cities. This is the last time I had a world record, 666. And in 1992, Applegate, Bixby, Quartal, and Cook started an enterprise Right now, probably 1,000 computers in the world are running on TSP problems in this enterprise. But you see the progress. The number of cities is 500 times bigger than 50 years ago, and the problem size is 300,000 times bigger. That's quite some success. And we are talking about 312 million integer variables that can be solved. And here's the pictures. So I would like to now advertise this. This is the group of 4 people. They have 15 years of code development. They gave a talk at ICM 98 about it and got a prize for it, actually, for a computational work. They've made their code available on the internet, Concord. You can download it and solve your own problems. And here's the first big problem solved in 1954. This is from my PhD thesis. That is my favorite problem, 666 cities in the world. I've seen about half of them. Ouro Preto is here, for instance, give you one example, because it's a wonderful place. Rio, of course. This is United States, 13,500 cities. And here's the branching tree. And the secret is that the gap between the LP bound and this is the upper bound, and that's the lower bound, is only 0.01%. Without that, you would never be able to solve it. And it's all cutting plane based. And that ran 4 CPU years on 50 workstations all around the world. And here is the world record until recently. This is the optimal tour of Germany. And that's the current world record. The optimum tour of Sweden. Sweden has, what was that, 25,000 cities. Here it's this number, 24,978 cities. Okay, and this is currently running. To 1.9 million, all cities in the world. They are down to 0.1%, and linear programming is the main driving force, and maybe in 10 years they have solved it. But what it shows, there's a stable algorithm. I mean, this thing doesn't break down. It runs on 1,000 algorithms in parallel, and it's still, you can prove in the end that this was optimum. Okay, now it's finished with how combinatorial optimizers do it. We come back to that later. I said astrology, astronomy, and the arts. And now I would like to get this program going, this computer running. I hope that somebody hasn't killed it. Okay. So in parallel, there is a linear traveling salesman running now. It's starting. And I will tell you, don't look at it all the time. It runs 8 minutes. Okay, so look at this picture. This is at 4:15 today, the sky above Rio de Janeiro. Well, if you switch off the sun, this is what you would see. I have a program that computes this. And here are all these constellations. And now if you invert the colors, so the stars are black and the sky is white, that's another picture of the sky above Rio. And the interesting thing is that people have always used graphs without knowing what graphs were. They were invented by Euler, but later on, of course, it's just the naming of that. And I would like to you to pay attention to these pictures. So these are named by certain persons that were important in mythology. Orion, Taurus, Gemini, Cancer, and Hydra, and so on. So people have seen these pictures in the sky. And of course, how did they see it? This was a piece of art. You know, they looked at the stars and they made figures out of it. And in fact, if you go through this, this is often traveling salesman solutions of that. That I found very interesting. So what you only see is these red lines, and the red lines are just graphs. But if you go into detailed analysis, so this is the analysis of the complete Orion picture, the celestial map, and the yellow dashed lines are constellation boundaries. You see, for instance, an epsilon here, the mathematics comes up there. There's a famous great Orion nebula. They all see this above our sky. And Orion actually comes from an Akkadian word, Uru Ana. And here's and what I would like to remind you, this is nothing but drawing by numbers. Now it's drawing by stars, right? They are taking the stars, and Orion is mapped onto the stars. And here's one of the pictures that I found in the internet. And you have the story behind Orion, the master of the winter skies, in his golden armor, and so on, and the dogs around him, and the chariot, and the twins, and so on. That's a very fascinating story, but different people see different Orions. That's another Orion that is from an old engraving in Uranometria. And you see here Orion, that's the grand Orion Nebula. The question is, can we still find new constellations nowadays? Well, people have observed the sky for a long time, and they have found constellations. So here I have a suggestion. We add the radio stars to because we cannot see them, that the optical spectrum, we have to go out of the optical spectrum. And then we look at pictures in the sky, and I would like to think we should start creating new sky mysteries like the ones about Orion and the dogs and Canis and so on. So IMU has asked me to give it a try. So look at the sky here above Rio. I showed you, this is right now the sky above Rio. And the first thing you spot a radio star formation. That's what the people have done in former times. They looked at there's a nice star constellation, and then they have found some good idea about it. Then the next stop is you run data analysis tools to detect good candidates of star formations for constellations. And actually, I looked at it, and I found 8,616 radio stars that looked promising for a new myth in the sky. Of course, how do you draw this? Well, you let combinatorial optimization find a good graph representation of the formation. And the best picture is the new constellation, of course. So what did I do? After I found this constellation, I ran traveling salesman algorithms, and I would like to declare now the best picture a new constellation. And you see the best picture coming up on the right-hand side in the sky. This is exactly the solution of the combinatorial optimization problem, the TSP, representing this formation. And so I have computed these 8,666 stars and ran it for a whole weekend. I could not find the optimum solution, but I could come up with a solution that is only 0.25% of optimality of my computer here. But I think that is good enough to have a decent picture and now declare it a constellation of radio stars. And this is the new constellation I would like to mention. Let us talk about Jakob Pallis here. And I would like to mention his work for the International Mathematical Union. I looked up some of his CV. He was member of the executive committee from 83 to 1990, became a secretary for 8 years, was president for 4 years, and was past president for another 4 years, and he had many other activities. So basically 25 years of devoted work for the traveling, for the IMU, traveling a lot. He was the traveling salesman of the International Mathematical Union. I looked up the history, and he has by far the longest involvement and the most intensive involvement of IMU. And I think Jakob's service to IMU is so outstanding that he deserves some kind of recognition for his unique contribution. And the recognition is coming up. I know his term is not over, but IMU, that means John Ball as the president thought this is a particular event, namely it's the last time the executive committee is meeting in Rio before Jakob retires from his EC duties. He will not retire, of course, but from this particular duties. And also he had his 65th birthday recently. And there will be some parade of honors coming up, and it's foreseeable. And this is the start of it. And what you can see here now is the final picture that is coming up live on the right-hand side. We could call it Jacob in the sky. Or there are other ways to say that. Now, if you take the stars out of it, that could be Jacob's true radio star portrait. Or the secret Pallis constellation, or briefly, the TSP constellation. So he was traveling so much that I thought I'd give him a traveling salesman solution. And here comes a printed version of it. So we have a real picture while this is finishing down there. Oh yeah, good idea. Okay. And the IMU hopes that this portrait will find a prominent location at IMPA. The interesting aspect of this is we are very close. You don't see anything, but you see it from the distance. I think it very much resembles Jacob. And this was found in the sky, and sky-high contribution. And thanks, Jacob, for all the work you did for the International Mathematical Union.
Thank you for that wonderful lecture. And are there any questions, first of all, about the lecture? Everybody is stunned, I think. So, in that case, in honor of Jacob, IMU invites you to have some refreshment. Thank you very much, Ross.